Okay, so we're graphing logarithms today, and the reason that we see these graphs up here is because I want to show you that logarithms and exponentials are inverses of each other. Okay, now if things are inverses of each other, then they reflect over this line. And what's the equation of this line?
X equals y.
Yeah, that's right, y equals x. Okay, so exponential growth, for the inverse of that, we just say that the log graph is increasing because as x gets bigger, y keeps going up. Okay, so this is whenever you have a base that's greater than 1. For exponential decay, the inverse of that is a decreasing log function, and that happens whenever your b is between 0 and 1, so like a half or 3/4 or whatever. We say that that's a decreasing function. All right, now, being inverses of each other, their asymptotes also like reflect over this line y equals x. So exponential functions had a horizontal asymptote. What kind of asymptote does this look like? Yeah, vertical. So these things have a vertical asymptote. The parent function at least has a vertical asymptote at x equals 0. Okay. Now, for not the parent function, if we just do it in the general form, y equals log base b of x minus h plus k. Okay, so we're going to leave out like an a for the day, so there won't be any reflections or anything like that. With an exponential, it was k that affected the horizontal asymptote, right? Whenever you move up or down. But now, since a vertical asymptote is up and down, it can move left and right. So this h is going to shift the vertical asymptote. So here, I'll even draw in these vertical asymptotes so we can see them. Okay, now for an exponential, what were the two main points that we always wrote down?
0, 1, and 1.
0, 1, and 1b. Alright, now for a log, remember that log is the inverse. So for inverses, what do you do to the points? You just reverse them. So for a log, my main points are going to be 1, 0, and b1. That's one of the main things for graphing. Okay, the next thing that we're going to talk about is the domain and range of a log. But we're going to do that by thinking about an exponential first. What was the domain of all those exponential functions that we just got done? All real numbers. And then the range was always y is greater than or y is less than the horizontal asymptote. Right? So wherever the horizontal asymptote shifted, that would be in our range. Right? It was always either greater than or less than that asymptote. So if the x's and y's are switching, right, got a domain and a range here. Let's talk about the range of a logarithm first. Since the x's and y's switch, the domain of an exponential was all real numbers, so that's going to end up being the range of the log. So it can go through all the y's. What do you think the domain is going to be? Yeah, so the domain is kind of like the exponential, except for we're dealing with x's that are greater than or x's that are less than the vertical asymptote. Okay, so let's try to graph y equals log base 2 of x. So the very first 2 points that I always care about are 1, 0, b1. If you're looking for a way to remember this, you could be like, oh man, I love logs. I'm hoping to someday be one. But that's a stupid way to remember anything. So Don't do that. What's the base of this log? What's the base of this log? 2. So we have 1, 0, 2, 1. Sitting on the side of a swamp, being a log. Frog sitting on you. All right. So, are there any shifts left or right or up or down?
No.
No, there's not. So, since there's none left or right, my vertical asymptote did not move. The vertical asymptote is still right here. And what's the equation of this line? X equals 0. Because during that entire line, the x never changes. It's always 0. Will this be will this increase or decrease? It'll increase in y. It increases because 2 is greater than 1. Okay, so let's plot our points. 1, 0. Now, if you don't have a nice graph, you could just plot that and label it 1, 0, 2, 1. And I'm going to draw my curve through. I know it's increasing. Okay. What's the domain of this bad boy? All of these x's are greater than 0. Right? The way you find that is you just look at your asymptote, x equals 0, and just change this either to a greater than or less than, depending on which way the graph is facing. So all of these x's are greater than 0. What's the range? All real numbers. Perfect. All right, now we're going to graph log base 1/2 of x minus 2 minus 1. So the base for this, well, let's write down. We have 1, 0, b1. What's the base of this log? It's a half. For graphing purposes, I'm just going to change that to a decimal 0.5. Okay, so will this be increasing or decreasing? Decreasing because your base is between 0 and 1. Okay, now, what does this minus 2 do? It goes right 2. So if it shifts right 2, what else moves? Does the asymptote move by the 2 or the 1?
The 1.
Does the 1 move the asymptote? Or does the 2? The 2. The 1 moves the asymptote for exponential. It doesn't move the asymptote for logarithmic. So my asymptote is now at x equals 2. Just draw a nice asymptote. All right. Since it shifts the asymptote right 2, it also shifts the points right 2. Does that affect the x or y coordinates? Yeah, moving left or right, just like this axis, it affects the x coordinates. So I'm going to have to add 2 to my x values. Okay, and then finally this minus 1, what does that do? That's your k, so this is a down 1. So I'm going to have to subtract 1 from the y values. So my final points are 2, negative 1. Oh, nope, 1 plus 2 is 3, Mr. Myers. Idiot. 2.50. So what's weird about logs is that now these points are kind of like in the wrong order, in the sense that this is further to the right than this point. But that'll happen whenever you have decreasing functions. So 2.50 and 3, negative 1. Draw our curve through that. It's decreasing, so it starts high, goes low. Okay, now what's the domain?
x's greater than 2.
All the x's that are greater than 2. Perfect. And the range? All the real numbers. For our last example, we're going to do y is equal to the natural log of x plus 2. Okay? So, I'm always going to start with my 1, 0, b1. Alright, now, the tricky part of this one is, what is the base?
E.
The base for a natural log is e. Okay? Whenever you don't see it there, the base for a natural log is e. So this is actually 1, 0, e, 1. So, like, little side note, if you saw the log of x, whoops, that's an ugly x. If you saw log of x, what would b equal? What's the base here?
E. No. E. 1.
Nope.
E.
X inverse of E.
All real numbers.
E.
It's
10.
E. 100.
Oh.
And
Yeah, so remember that this is called a common log if the base is 10, and natural log is base e. So this will come up a lot. You have to remember that. Okay, so what's e?
It's a number. It's like 2 point something.
Yeah, we'll use 2.7. All right, and the only transformation here is that this moved up 2. All right, so that affects the y's. So I'm at 1, 2. Where'd the 1 go? And 2.73. Okay, did the vertical asymptote shift at all?
nope.
No, so it's still here at, what's the equation of this line?
X. 1.
X is equal to 0. Okay, I plot the points 1, 2, 2.73. Draw my smooth curve through it. Not gonna mess up. Alright. This is smooth enough. And then I say my domain is all of the x's bigger than 0 because it's all to the right of that x equals 0. And the range is all real numbers. Alright, so it's a lot like graphing exponentials, right? So if you can graph exponentials, you can graph logs. Alright, goodbye.